Okay, hello, Maurits here again. In the previous video we solved this problem of the velocity and the period of this particular conical pendulum. We should try to make a general formula for this. So we start with the observation yet again that the period equals to 2 pi L sine theta over v, and now we replace our velocity with a general expression, so we get 2 pi L sine theta over square root of g L sine theta tan theta. And here we can simplify this a bit. We can do like this, right? 2 pi square root of L square sine square theta over square root of G L sine theta over cos of theta, right? And then we can combine these two square roots, and we can see we can do a bunch of simplifications. The sine square theta will cancel against these two, and we get one of the L's disappearing there, and when we can multiply both the numerator and denominator by cos of theta, and that will end up with 2 pi square root of L cos theta over G. So that will be our expression for the period, and we can indeed do a calculation of this. So we take the length 0.12 times cos of 30 divided by 9.81, and by the way, remember to check that you are in radians degrees when you're doing this. Shift square root of shift ounce times 2 times shift pi, and we get the same answer as before, about 0.65 seconds. For small angles, so if theta is approximately 0, we have that cos of theta is approximately equal to 1. So this will then make the approximate formula 2 pi square root of L over G, which is the same formula as for the plane pendulum. So are these two basically the same? And for small angles they are. This will give the same period as this, very closely. But for big angles, say about 90 degrees, this is the plane pendulum, but if I take the conical pendulum, I need to increase the speed, and the time will approach 0. It will go faster and faster and faster. To actually reach an 80 degree, I would need to go infinitely quick, right? The reason for that is, if you think about this, if the angle, the component of the force inward, as we saw there, will be, this must be so that if we split this in two components, so now we continue this force down, this in some way have to be equal to big of that. You can see that the tension will be extremely high, and that means that the inward force is extremely big, and that means that the period is very, very short. So, how good would this approximation be for 30 degrees? Let's see. We take 2 times shift pi times shift square root of bracket 0.12 over 9.81. Not very good. 30 degrees is a bit too big to angle to use this simplification here, this approximation. And we can so anyhow, that was a more general formula for this this problem, that will be the formula, and for small angles it will basically be the same as for an ordinary pendulum.